Hello everyone, and welcome back to this series on complex analysis, and today we're going to be continuing our exploration of functions whose domain can be taken as a set of complex numbers and discuss some important properties associated to them. So what I want to do first is just go over some of the basic functions that we have up to this point and a couple important properties about them. So the very first property that you definitely should know would be properties of the natural logarithm inside of the complex plane. Now remember, we realized that the complex exponential function e to the z was a periodic function, and that's going to force its inverse, the natural log function, to be multivalued. And we were able to prove that the natural log of z under the branch of k to be equal to the natural log of the magnitude of that complex number, provided it's not 0, plus I times the argument of that complex number plus 2k pi I. Right? And keep in mind the 2 pi I was the periodicity for the exponential function. And also, we investigated briefly how powers work in the complex plane. We realized that in some sense, powers in the complex plane not only scale objects, but rotates them. So if z to the power of n is equal to 1, then there exist n unique values, in particular n unique type of numbers. So where does these objects belong? So unique z belonging to the set of complex numbers such that z to the power of n is equal to 1. And these n unique objects are referred to as the nth roots of unity. So the nth roots of unity. Right? And why do we call it the nth roots of unity? Because in some sense it's baiting, well, how do you take square roots, cube roots, fourth roots, in particular of the number 1. So that's the unity in that expression. So let's just go through a quick numerical example just to make sure we have these under wraps. So suppose we have z to the power of 8 is equal to 1, and we want to find all complex numbers z's that satisfy this. So if z is written in polar form, we can write this as r e to the I theta. Then we can write our equation, r e I theta to the power of 8 will be equal to, well, r is going to be a real number, and we can write that as r to the power of 8. And then we can have e to the I 8 theta underneath the norm. And that's obviously going to be equal to, since that's just cosine something plus I sine something. And once you square that and then take the square root, you're going to get the square root of 1, which is 1. That's just going to give you r to the power of 8. And since we're solving the equation, z to the 8 is equal to 1, we have that all of the solutions need to satisfy this equation in terms of its magnitude. And there's only one real number, r, that's non-negative, that satisfies that. And that's going to be r is equal to 1. So that means what? So that means all solutions, in particular all 8 solutions, have a magnitude equal to 1, because keep in mind the magnitude of z is represented by r. So once we have that, then we're like, okay, well that means that z must be equal to e to the I theta once we re-represent it. So that means z will be equal to e to the, and keep in mind we derived this property already before, 2k pi divided by m, where n in this case is going to be equal to 8. So using the Euler-Cotes identity, we can write this as the cosine of k pi divided by 4 plus I sine k pi divided by 4. And keep in mind k is going to belong to the set 0, 1, 2, all the way down to n minus 1. In this case, that would be equal to 8 minus 1, which would be equal to 7. And we will write the 8th root of 1, or denote this as the principal 8th root of 1, which is equal to 1, which is one of the solutions. Okay. So if we were to graph all of these solutions, then the angle between each of them will be equal to 360 degrees divided by 8, which will be equal to 45 degrees. That's going to be that k pi over 4. So if we just draw a real and imaginary axis, so the real part of z and the imaginary part of z, and since that all magnitudes will be equal to 1, then all of them are going to be lying on the unit circle. Right, so there's your 1, 0, and there's your 0, 1. So where will all of our solutions be located? So the principal root will be located at x is equal to 1, y is equal to 0. And then we're going to be rotating by 45 degrees. So the next solution will be there. 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 The next will be there. The next will be there. And the last will be there. Right, so those would be all of your solutions. So that would be your plus or minus root 2 over 2 plus or minus root 2 over 2i, in addition to your plus or minus 1s, 0s, and your 0 plus or minus 1s. So those are going to form your solutions. And if we were to connect each of these, then all of those distances would be equal to each other, and then you would get a regular octagon in the xy plane. Right, so those would be your 8th roots of unity located at each of those vertices of your polygon. Right, so there is some geometric beauty associated to a lot of these results. All right, so let's just state a theorem that kind of solidifies what we've done so far. So if z belongs to the set of C and z to the power of m is equal to 1, where n is a natural number. And this is going to be very important because if n is a complex number, then you actually get a little bit more of a difficult behavior. Then the set of all solutions, which I'm going to represent as S, which is the set of all z such that z is equal to e to the 2k pi I over n, where k belongs to 0, 1, 2, all the way down to m minus 1, is the set of all solutions to our equation. Right? So that's pretty much what we've been working with so far. So obviously we know how to take the 5th root of 1, the 8th root of 1, and we also know how to solve natural power exponential equations when they're set equal to 1. But what if we want to solve, say, z to the power of 5 is equal to 3 plus I? Obviously, this theory doesn't give us that. So we need to possibly extend our ability to be able to take radicals of any complex number. All right, so let's just introduce a bit of notation. So I'm going to define the nth root of the number 1 to be equal to e to the 2k pi I divided by m. Notice that I'm defining a function rt superscript n subscript k. So this is actually going to focus on what we call a particular branch of our radical function, because there's multiple roots of a particular number. At least there's multiple nth roots provided n is greater than or equal to 2. So we're going to have rtn k1 is going to be defined to be equal to this particular number, where k belongs to, again, 0, 1, 2, all the way down to n minus 1, with rtn0 of 1 being defined to be, in terms of notation, this particular object, which you're already familiar with from basic real variables, and we already know that that's going to be equal to 1, also in the realm of real variables. So this object, in addition to its notation, is referred to as the principal nth root of 1. Why is it the principal nth root of 1? Because it chooses a particular root of 1, in particular the 0 branched root of 1. So this particular function, so this is the principal what we call branch of rtn k. So the principal nth root is a particular number that the root function supplies, and the principal branch of a function is a particular function that generates particular values. In particular, principal branches of functions generate principal outputs, in this case, the principal roots of functions. Right? So if you want to choose, for example, k to be equal to 1, that's not the principal root. You can say it's the next root in succession. Obviously, you wouldn't call it the secondary root or the first root, because then people would get confused with the word principal and what it means in the natural language. So obviously we know how to take the root of 1 and how to find all of the nth roots of 1, but we want to extend that to other numbers. And now we have this notation that we want to extend to. So let's just recall a couple things from natural logarithms in the complex plane. In particular, the natural log, or the kth branch of the natural log function, is equal to the principal branch of the natural log of the magnitude plus I arg z plus 2k pi I. And again, k belongs to the set of integers in this expression. So what we want to do is we want to define the principal nth root of z, not necessarily 1. So this is going to be the principal nth root of z. And how we want to define it? Well, obviously we want it to be in parallel, or an extension of, the real variable properties that we have. So what we're going to do is we're going to define this object to be equal to e to the power 1 over m times the principal natural logarithm of z. Right? And you might be thinking, well, why would I define it to be this? Well, keep in mind, if all of our properties hold for logarithms, and in this case they do, this is going to be equal to e to the natural log of 0 of z to the power of 1 over m. And obviously some people will use this expression as z to the power 1 over m as an alternative notation. So we would like this e in that natural log to cancel, which they do naturally even in the complex plane. So this is how we're going to define this particular notation, in particular how to define the principal nth root. We're going to define it as e to the power 1 over n times the principal natural logarithm of that complex number for which we're trying to take the logarithm of. And you're like, okay, well, do I know how to work with that particular expression in the complex plane? Of course we do, because z can be represented as x plus iy, and we already know the definition of the natural log of 0 of z from the principal definition of ln kz. So we can write this as an alternative of e to the 1 over n times the principal logarithm of the magnitude of the number we're trying to take the radical of, plus I times the argument of that complex number we're trying to take the radical of, plus 0 pi I, which is just going to be equal to 0. So that completes the definition of the principal nth root of z. Right, so the principal nth root is defined in terms of the principal branch of the natural logarithm. So obviously that's the principal nth root. What if you don't want the principal nth root? What if you want the third nth root of a particular number? And obviously those are just going to be rotations of the principal nth root. So from here we're going to define the general radical of a particular number. So Rtnk of z will be defined to be equal to the principal nth root of z multiplied by a rotation function, in particular the complex exponential. Right, and again, k will range from 0, 1, 2, all the way down to n minus 1. Right, so this is going to be our newly defined function, the complex multivalued radical function, and it's going to solve exponential equations for us. So now let's actually do an example of this just to make sure we understand how to work with it. So now let's see if we can solve these, say, polynomial equations in the realm of the complex plane. So in particular, let's use this example, in particular z cubed is equal to I, and see if we can find all solutions that satisfy. This is obviously going to be a watered down version of how to solve general polynomial equations in the realm of C, but this pretty much gives us all the basics that we need to do aside from factoring and all those other theorems that you may have learned in pre-calculus. Right? So what are all of the solutions of this function representable as? Well, if z cubed is equal to I, that means z will be equal to the cube root of I, and that's obviously going to be multivalued. And here, since our power is equal to 3, k is going to belong to the interval 0, 1, and 2. All right, so we're going to have 3 solutions to this particular equation. And again, this process does not necessarily work as directly if that power on z is, say, 3.5 or something that's not a natural number, and we'll get to that a little bit later. So if z is equal to the cube root of I, the kth branch, we can represent this as the principal cube root of I multiplied by e to the power of 2k pi I divided by 3. So pretty much all we need to really find here is the principal cube root of I and then rotate it by 2 pi over 3. So once we do that, what will we get? So, well, how do we find the cube root of I? So that's going to be equal to, by definition, e to the 1/3 times the principal logarithm of the magnitude of I plus I times the argument of I, which we know to be pi over 2. And then we're going to multiply that by e to the power of 2k pi I all over 3. So what are these components equal to? So the magnitude of I is going to be equal to 1, so that's going to vanish and turn to 0. And then we're just going to be left with this I pi over 2 term inside of our brackets. So that's going to be equal to e to the, what would that be? That would be I pi over 6, then multiplied by e to the power of 2k pi I all over 3. We're going to be adding these powers, so it's going to be important to just get a common denominator for this. So I'm just going to go ahead and multiply that by 2 so I can get a common denominator of 6. So this is going to be equal to e to the I pi divided by 6 multiplied by 1 plus 4k. And those are going to be our solutions for our equation, right? At least in polar form. Right? So again, k is going to belong to the region 0, 1, and 2. So let's actually list out what these values are so we can get a handle on what they are. So when k is equal to 0, that's going to give us z is equal to e to the I pi over 6. When k is equal to 1, that's going to be z e to the I 5 pi over 6. And when k is equal to 2, our next solution is going to be z is equal to e to the I 9 pi over 6, which is going to simplify to e to the I 3 pi over 2. So let's actually take a moment and sketch these graphs out. So what are going to be their magnitudes? Keep in mind, notice that r is going to be equal to 1 for all of them because the magnitude of I is going to be equal to 1. So that means all of them are going to fall onto your unit circle. So keep in mind, what is this pi over 6? That's going to be the argument. So in degrees, that's going to be 180 divided by 6. That's going to be equal to 30 degrees. So we're going to have our 30-degree angle located here, forcing our first solution to be there. So that's going to be our principal root of I. And then we're going to rotate or split the interior angles of this triangle by 3. So 3 is going to divide into 360, 120 degrees. So 120 plus 30 is going to give us 150. So that's still going to have a 30-degree reference angle, so this picture should look relatively symmetric about the vertical positive y-axis. So there's going to be our next solution. And then 3 pi over 2, that's going to be located down here. So there's your next root, or the first root of I, and down here that's going to be equal to RT32 of I. So if we were to connect these vertices together, what shape will you get? You will obviously get a little sign that looks like that, in particular the equilateral triangle symbol. Right? So that's how you would solve basic equations of this form, and other exponential equations with natural powers will follow the same exact pattern. So recall from previous discussions that the sine function is defined as 1 over 2i times e to the iz minus e to the minus iz. This definition, in connection with its Taylor series from real variables, kind of gave us the intuition that e to the z was going to be periodic because it can be represented in terms of sine and cosine. So obviously from this, we were able to derive several identities, in particular e to the iz being periodic, which means that if e to the iz is periodic, then so is the function sine of z. So if sine of z is periodic in R, then here we see that it's going to be periodic in C. So that means if we decide to define the inverse of sine of z, so in particular arc sine of z, well, when we tried to define the inverse of e to the iz, which was periodic, then its inverse, the logarithm, became multivalued. That means arc sine of z will also be multivalued. valued. So let's see if we can go ahead and define the arcsine function in terms of its branches, and then go ahead and define a principal branch for it so we can work with calculations. All right, so how are we going to go about this? So what we're going to do is we're going to go about it in a let's solve this equation type of way. In particular, let's assume that w is equal to 1 over 2I times e to the iz minus e to the minus iz. So this is obviously going to be equal to the sine of z. And what we want to do is we want to solve this equation for z, and hopefully we'll get an expression and then define that as the inverse sine function. So what I want to do once I have this is I'm going to let or multiply both sides by 2i. That's going to give us 2i omega will be equal to, and let's just use a nice little u substitution. Let's let u be equal to e to the iz, just to make things a little bit more nicer to look at. That's going to give us u minus 1 over u. So our goal is to write this as a quadratic equation in terms of u, and then solve it via the quadratic equation. So once we have that, that's going to give us what? So that's going to give us u squared minus 2i omega u minus 1 will be equal to 0. And then we can solve this equation for u. So u will be equal to 2i omega, and then we're going to have plus or minus the square root of minus 4 omega squared plus 4 all over 2. And then we can factor out a 4 outside a radical and then cancel a 2. And then we're going to have I omega plus or minus the square root of 1 minus omega squared. So that's going to give us u, and then we can resubstitute back. In terms of our substitution, u is equal to e to the iz by taking the natural log and then dividing by I. So we're going to have that z will be equal to 1 over I multiplied by the natural log base k. Now keep in mind that base k is the branch of the logarithm. It's not like a base like log base 5 or log base e or something. Then we're going to have I omega plus or minus the square root of 1 minus omega squared. And we can multiply top and bottom by I, and then we're going to have minus I times the multivalued expression, natural log of k, of I omega, plus or minus the square root of 1 minus omega squared. Right? Now, it's very important in this expression that we remember what the argument ranges from. In particular, let's note that the argument of z is defined to belong to the interval minus pi to pi. Now, some people will take a different preference for this definition of the argument depending on what function they're working with. But in particular, for the log function, we're going to have a branch cut on the negative real axis, so we want to avoid the negative real axis, so we're going to be choosing the argument in here. So if we look at the graph of this and want to define this in a nice way, what we want is to sort of be able to revolve in that counterclockwise direction and sweep across all of these particular values. And this is going to be used in the definition of the natural log of z. So this is used in the definition of the natural log of z. Right? So it's very important because notice that this is a multivalued expression, and we also have a plus or minus, so in some sense we have a two-tier multivalued expression. But keep in mind, since we're adding multiples of 2 pi I, if we take our definition to be equal to the positive one, we can actually get the other solution to this particular equation by choosing a different branch of our logarithm function. Right? So with that particular preference, instead of defining it as the minus sign, which is going to put us on the negative real axis, we're going to define the principal branch to be the one that's on the real axis. And this is going to follow in preference. For example, what would you define the square root of 1 to be? Well, some people will say, oh, I'm going to define that to be equal to negative 1. And I can define, for example, the second root of 1 to be equal to positive 1. So that means, okay, that means your principal square root of 1 is going to be negative 1, and then your secondary root of 1 would be on the right-hand axis. I mean, more power to you if you want to define it that way, but Usually it's not nice to sort of put principal values on the negative real axis because that's going to create issues for your natural logarithm. So we usually do not follow that convention for that particular reason, right? So we're going to choose it on the positive real axis so we don't have any issues with our logarithm and evaluations on it. Right? So let's go ahead and define our arcsine function now. So the arcsine of z will be defined to be equal to minus I times the logarithm of iz plus the square root of 1 minus z squared. Technically speaking, you can subscript this with k since this is a multivalued function, but usually if you don't script natural log in the arcsine function, usually it's already assumed that you know that this is a multi-valued function, just like the other ones that we have discussed before. So we have defined the arcsine function. Well, can you do that for the arc cosine function? Of course you can. Using a similar way, we can find that the arc cosine function of z can be defined to be equal to, as long as it stays consistent with your definitions, which keep in mind is e to the iz plus e to the minus iz all over 2. So that's going to be equal to minus I times the natural logarithm of z without the I plus, and then the interiors swapped, z squared minus 1. And also we're going to have our arctangent inverse function. This is a very important one. And this will be defined to be equal to I divided by 2 times the natural logarithm of 1 minus iz all over 1 plus iz. Now obviously this is going to have a couple issues. For example, if z is equal to positive I, then we're going to have I times I, which is I squared, which is negative 1. So that means the bottom is going to go to 0. That's a problem. And if you go negative I, then you're going to have 0 on the top. That's going to give you the natural log of 0. That's also a problem. So z cannot be equal to plus or minus I in the definition of the inverse tangent function. And keep in mind all of these inverse functions are multi-valued. So those are for our circular functions. Can we define inverses for your hyperbolic counterparts? Of course you can. So the inverse hyperbolic sine function will be defined to be equal to, in a similar way, the only difference is the I is not going to be out in front, because you might remember that the hyperbolic functions are actually a little bit more nicer to work with compared to the circular counterparts. So it's going to be equal to the natural log of z plus the square root of z squared plus 1. And then we're going to have our inverse cosine function defined in a parallel world in terms of the real world counterpart. And this is going to be equal to z plus, do you remember? Z squared minus 1. And then the hyperbolic tangent function, arc tanh of k. This will be defined to be equal to 1/2. This has a lot of applications in practice. The natural log of 1 plus z all over 1 minus z. There's some obvious restrictions of what z cannot be here. Z obviously cannot be equal to plus or minus 1. All right? So now we have actually quite a few functions already defined because we know how to deal with radicals and powers and their multi-valued nature. So let's just close this conversation out with a nice little calculation example. Suppose somebody asks you to find the inverse hyperbolic tangent of 1 plus I. How would you find it? You might want to take a moment, pause this video, and see if you can calculate this on your own. So from the definition that we could derive, that's going to be equal to 1/2 times the natural log, and keep in mind this is going to be a multi-valued natural log, of, so 1 plus 1 plus I, that's going to be equal to 2 plus I, and on the bottom we're going to have 1 minus 1 minus I, which is going to be equal to minus I. Now, we have that minus I on bottom. That's not exactly exciting, so what I want to do is just multiply top and bottom of that expression by minus I just to clean things up a bit. So we have the multivalued logarithm of, so we're going to have minus 2I, and then minus I times I is going to be minus minus 1, that's going to be plus 1, and minus I times minus I is plus I squared, which will be equal to minus 1. So that's going to change the signs of your numerator to 2i minus 1. So we have 1/2 times the natural log of 2i minus 1. All right, so things are looking great so far, so let's keep on going. So this is going to be equal to 1/2, and then we're going to use the multivalued nature of the logarithm definition. So that's going to be equal to the natural log of the magnitude of that, which is going to be equal to the square root of 2 squared, which is 4, plus 1 squared, which is 1, so that's going to give us a square root of 5, and then plus I times the argument of 2i plus 1. So where is 2i plus 1, or minus 1 plus 2i? So minus 1 plus 2i is going to be located here somewhere, right? So that means the argument of this complex number is going to be that angle there. All right. In particular, it's going to be the arctangent of 2 divided by negative 1. So that's going to be the arctangent of minus 2 over 1, or just minus 2. Right? So once we have that, let's not forget everything. So the argument of 2i minus 1, and let's not forget our 2k pi I, our periodicity term. And that's going to be equal to who? So 1/2 times the natural log of the square root of 5. And let's actually distribute our 1/2m. So we're going to have plus, let's see what we have here. So plus, we can write that as I over 2. Let's actually factor out our entire I out of our expression. So 1/2, we'll put I on the right-hand side. Then we're going to have the arctangent of minus 2, and then plus 2k pi, and then I. All right? So that gives us our, and keep in mind this object belongs to quadrant 2, just in case you have a calculator that doesn't force that for you. So that's going to give you your arctangent, your arc hyperbolic tangent, kth branch, of 1 plus I. At least that's the analytical form, without any further simplification that you could do. For example, you could maybe rewrite arctangent of minus 2 if you really want to. All right? So that means the principal branch of the hyperbolic arctangent of 1 plus I will be equal to 1/2 times the natural log of the square root of 5, and then plus 1/2 times the arctangent of minus 2i. So there's the real part, there's the imaginary part, and then you can use a calculator to numerically represent this, and one can find that's approximately equal to 0.4024 plus 1.0172i. And you could also find the secondary branch of this number by just adding your 2 pi I at the very end. But that would be your value for this expression. And similar calculations will follow for the other functions we defined. So I hope you enjoyed this video, and I'll see you in the next one. Take care.